University. Welcome to the ESE seminar series, and this is the fifth this semester. And the topic will be energy storage. Uh, the ones who have attended these seminars, you know the theme for this semester is energy transition. We heard two talks previously from people representing the transitions in Uruguay and in India, and you saw that the pathways were very different. And you hear two more in the end of the near the end of the semester, where they'll talk about the strategies in Europe and in Australia. And the common theme in all these transitions is the use of energy storage or batteries, and is a common theme in the worldwide strategy towards transitioning from the traditional grid to the decarbonized. So, what we'll be hearing about today is energy storage and the different usages, and the presentation will be made by Eva GARDOW with EPRI. Before she joined EPRI, Eva was leading energy storage research at First Energy and has played a significant leadership role in the industry beyond that, including serving as a long-term board member of the Energy Storage Association, as well as serving presently as a board chair for the New York Battery and Energy Storage Technology, NY BEST as it's called, consortium. Welcome, Eva, and the floor is yours.
Thank you so much, Rudy. Hi, everyone. Just do a sound check. Everyone can hear me okay?
Yes.
Very good.
Yes, we can.
Thank you so much. So as Rudy mentioned, my name is Eva GARDOW. I'm a program manager at the Electric Power Research Institute, known as EPRI. And I wanted to just take a moment and give you a little background on EPRI and all these other things. So we are going to cover these 8 topics. EPRI and what we do with battery energy storage at EPRI, because we actually have 2 research programs on energy storage, which I'll get into in a minute. Then I'll give you some background on why energy storage is important, which it sounds like you might already know. Then I'll go over some technologies and how we assess them, and then how they can be used, and then some details around battery energy storage system deployment, otherwise known as BEST deployment. And then some work we've done at EPRI to identify the roadmap for energy storage, battery energy storage, what needs to be done in the next several years in order to have a viable, commercial, safe, reliable energy storage asset. And then I'll wrap up with other EPRI energy storage resources. So, in this discussion, which will be technical, as well as some policy, and also give you ideas for your futures, what you might want to do in energy storage. So for those of you who don't know, EPRI is a leading global energy R&D collaborative. It was started in 1972, that at the outcome of the 1965 blackout in New York City. There were several congressional hearings done between 65 and 72, and essentially, the fundamental choice was more regulation or do something that so we don't have blackouts again. So the utilities got together and they asked Chauncey Starr to lead this R&D collaborative. And basically, we do collaborative research across utilities around the country and now around the world. And we are advancing energy technologies, including energy storage, through a multi-million-dollar collaborative research with 450 utilities, government offices, and having to do with production, delivery, and use. And that includes everything from protecting endangered species. We are an independent, not-for-profit collaborative and do a lot of public benefit research. So what do we do at EPRI in energy storage? So we've been working for 50 years in energy storage. And the group that I'm in, the research group that I work in, is called the Energy Storage and Distributed Generation, and it looks at primarily, battery electrochemical energy storage. But there's another group that, because there's just so many different technologies and ways to use energy storage, we have another group that does thermal and mechanical. My favorite analogy is, I'm going to tell you to go buy a box. And what kind of box would you come back with? And basically, that's energy storage. That box is lots of different sizes. I mean, if you think about batteries, they take the chart, keep your magic machine going. But what we're doing here is looking at what EPRI has done with AC energy storage. So we started with flow battery testing back in the 80s. We did SMES in the 90s. We did a lead acid system also in the 90s. We worked with the Department of Energy to develop the Handbook of Energy Storage in the early 2000s. We supported the No Trees energy storage system that Duke put in the 10s. I did a zinc bromide battery testing in 2006, and that was a follow-on that EPRI did one in 2008. But one of the most fundamental things we did was develop the DERVET, which is a techno-economic tool that was started in the 90s, but it has seen many iterations. It started out as StorageVet, but now it is the Distributed Energy Resources Value Estimation Tool. And that is a tool that is a free download. And now we're looking at long duration. We are testing an energy system. We're also working with utilities with CM Blue. So there's lots of different technologies that we are looking at now. And we are working with utilities, with vendors, and with government funding in order to advance energy storage research. So I wanted to just tell you how we've structured our research at EPRI. And the reason I'm telling you this is, one, it's a good way to organize things. And the other is because we have used this structure to develop our energy storage, or our battery energy storage roadmap, which I'll share with you later, which is a document and tool that you can download and learn even more later. So essentially, the two topics at the top span all aspects of energy storage, which is the first one is strategic intelligence. And then the second one is safety, because as we all know, when it comes to the utility and our life in general, safety comes first. So those are kind of two all-encompassing topics. But then we've delineated the rest of the research work based on technology evaluation, techno-economic analysis, deployment and operations. And then we kind of have a catch-all at the end, which is customer energy storage, microgrids, and distributed generation. And in many cases, that distributed generation is fossil fueled, but we are also working with low carbon distributed generation. And one reason we look at that is because there is a need for that, and often it ties in with energy storage and solar for microgrids. So we need to have research on all of that. So I'm going to get into some background overview information on energy storage. And this is the starting point. Why? Why do we need energy storage? So there are, as many of you know, strong policy and corporation goals for having a carbon-free grid. And yet we want to have and maintain the same reliability, or better than we have right now. So we are working towards achieving 100% renewable with net zero carbon goals for the grid. And so in order to be able to do that, we need to have this energy storage tool that can be a buffer. It can be storage, and help provide flexibility and stability to the grid. So those are some of the key drivers for energy storage. the evolution of utility needs. But at the same time, we really couldn't use it if we didn't have the technological advancements and fundamentally the decrease in cost. So if you look at the bottom right, that is, essentially a graph of where we're seeing the price of lithium ion. And we use lithium ion, because it's the belle of the ball right now. And the electric grid can really thank the consumer products industry and the magic machine for the development of the lithium ion battery. And just for your little history lesson, some of you may know this, but the lithium ion battery was developed as we know it today in the 70s by a team of 3 who got the Nobel Prize in 2019. And that would be Stan Whittingham, who lives in Binghamton, just up the road from you guys. He's at University of Binghamton. And then there was Mr. Goodenough, who was an American, but lived in Britain. Stan is a Brit who lives in America. And then there was another gentleman from Japan, I don't recall his name. But they developed the technology, the basis of what we use today. And what's interesting is that they really wanted to get it to be manufactured here in the States or in Europe, and there were no takers. So I don't know if anyone can guess who developed the lithium-ion battery, but seeing I can't see you or any chat, I'm just going to tell you, and that would be Sony. The Sony Walkman is the one who developed it. And now, because of that, so much of our manufacturing of lithium-ion batteries is in Asia. But there is a strong funding and interest to work to get that in the United States. And in fact, Binghamton is a center. It's called New Energy New York to work to develop lithium-ion batteries. There's also some being done in other parts of the country, Detroit also. So that is really, the drivers of energy storage are a combination of technology, cost, to being able to manufacture it in lots of places, and of course, both utility and customer choice and engagement. So it builds on it. And because of that, we are seeing policy and regulatory rules and shifts. So there are certain states that are more aggressive than others in their policy, and really California and New York, which is rather typical. And so California has been using energy storage for quite a number of years. And this was really an amazing day last April when energy storage provided power to the grid for about 2 hours, and see that little green section. So these are a series of graphs on how much renewables were being used and how much energy storage. But this colorful graph on the bottom, you can see across the bottom the different technologies that were providing electricity supply to the grid. And you have your nuclear foundation and your geothermal that really aren't in a position to do load following. And then all the yellow is the solar. And then once everyone got home and wanted to cook dinner and watch television, the sun went away, and so batteries stepped in and took over that large portion. And so we will see that more and more as energy storage gets integrated into the grid. It will become integral to the operation and the reliability of the electric grid. So this is a little more detail on the need and where we're at. So we're looking at the global energy storage capacity growing by hundreds of %, with China and the United States leading those deployments. But then there's lots of other parts of the world, with Latin America. I was just down in Mexico in August, and they are working to deploy solar plus storage. And the U.S. also has a lot of state goals. So as I had mentioned, California and New York are kind of first, but then if you look at the graph over on the bottom right, you can see some of the goals for other parts of the country that are really advancing the energy storage growth. So I just wanted to mention that, Wood Mackenzie partners with the American Clean Power Association, and they have a quarterly energy storage monitor where they evaluate what's been done and what's going to come down the pike. So they address the deployment growth and cost reduction. So in the second quarter, they just put out their monitor for the second quarter of 2024. And you can see battery energy storage deployments grew in the US more than 3 gigawatts or 10 gigawatt hours, up 74 to 86% respectively. And so this is really for the second quarter is the most. There was, I think last quarter in 2023 was the highest ever. But that's not unusual because of the way incentives are driven deployment. But to have the second quarter be so high is not typical. So we categorize energy storage into essentially three or four groupings, and we have utility scale, which is not necessarily a specific size, but utility owned and operated, front of the meter. And then you have behind the meter, which is categorized by commercial and industrial, and then residential as a separate category. Now, there is a lot of work being done on community solar too, but in most cases that gets lumped in with commercial and industrial. But as you can see, 85% of all the new capacity that was deployed in Q2 was in California, Arizona, and Texas. And for the smaller systems, the Tesla walls and such as those, the deployment pace has slowed down a little bit, but you're seeing that in California, Puerto Rico, in order to repower them after several hurricanes, and Hawaii. And what's important is the average price of a grid scale energy storage has declined 4% from Q1 to Q2, and then drastically from last year to this year by over 30%. And what's really great is this potential for U.S. domestic investment in battery energy storage system projects. And I don't know if you guys watch or keep track of the Department of Energy projects, but they have issued, I think, 3 long duration energy storage pilot funds. And EPRI works with several utilities and with vendors. So for example, I'm a project manager with a company in New York State called Urban Electric Power, and we're partnering with them with a NYSERDA, which is New York State Energy Research and Development Authority project, for a 100 kilowatt long duration 10-hour system. And then we are partnering with UEP and New York Power Authority on a Department of Energy project, which is deploying 2 other systems of equal size. So there are lots of different companies and lots of different projects like that, and you can access those project information just by Googling, Department of Energy energy storage projects or long duration energy storage projects, depending on which ones you're interested in. So I just wanted to take a moment as part of this Wood Mackenzie report. They take what's been deployed, and then they look out 5 years. So there is the expectation that the deployment will grow up to 42% between this year and next year, but then things will level out a little bit before growing again later in the decade. So this is looking at both capacity and energy, outlook. So anyhow, I think you can see the numbers, but we're looking up by 2028, 75 gigawatts in the US, which is it's not as big as one of the larger nuclear power plants that are running, but the power plants really these days are being made between 300 and 500 500 megawatts. So this is quite a significant amount. So I just wanted to take a minute before I move into technology to see if anyone had questions. We will reserve extra time at the end for questions that you don't have to think of them now, but you can certainly put your question in the chat box and Rudy will read them to me. Or you can come off mute and ask questions if you'd like.
All right, questions? Please unmute yourself, introduce yourself, and ask the question or drop it in the chat box as Eva suggested. Questions?
And if there are no questions, we can move into the technology sections. What do you think?
Eva, there is a question.
Okay.
From Joe Andrusani. The goal was net zero. Oops, I lost it. What happened? The goal was net zero. How does nuclear fit in?
That's a very good question. So as you saw in that one graph, nuclear, is kind of a base load. And there has been a lot of work to repower old nuclear stations. And at the same time, there's been quite a number that have been closed down. For example, Indian Point, just up the river on the Hudson River in New York. But there is work on a modular nuclear power system. And I believe the first one an order has been placed. So I think they're 300 megawatt size, and they're basically working to manufacture them and then work to site them. So I think the actual path nuclear forward is still being determined, but there are a lot of factions that were saying that you really can't do a net zero without nuclear. But from a policy perspective and from an actual perspective, it remains to be seen. But it seems like it would make some sense. So Rudy, any other questions?
Well, none so far. Any questions for Eva? We'll press on otherwise.
Hi, my name's Spencer. I'm an undergraduate student. And I was wondering if there are any energy storage management systems that are being developed and like which ones are most
So controls. Thank you, Spencer. So, nothing works without the control system. And when it comes to that control, there's energy storage systems typically have a hierarchy of control. You have to not all technologies require it, but it makes for a better operating system to have a battery management system, regardless of the kind of battery you have. We were actually working with one vendor where they said we didn't need a BMS, and so we tested without it. But after that test, they realized that it would work better with the BMS, and so they were working on it. So the BMS is very typically made by the battery manufacturer, although there are some that are, quote, off the shelf. And then that BMS needs to talk to the energy storage control system, which then needs to talk to the utility EMS, energy management system, and or get signals from the independent system operator controls. So there have been a couple of companies that have focused on control systems. One of them is called GELI, G-E-L-I, and it stands for something, and I can't remember what that is right now. But for the most part, a lot of the controls for the whole energy storage system is done by the integrator or the product developer. But one of the issues and concerns about that, and it's one of those researcher gaps that we've identified in our roadmap, our battery energy storage roadmap, is that a lot of those control systems are proprietary. They're not necessarily mapped the same. So there's an organization called MESA, which is, see if I can remember what that stands for, but it's Energy Storage Architecture, Modular Energy Storage Architecture. And you can look them up, and they have been working to try to develop a standard architecture so that different brands, different technologies, different integrators can work to talk together and essentially be in the same fleet. We're not there yet. You can help that happen, Spencer. So if you like controls, there's a lot of work there. So, you know, and a lot of times the people who are developing the fundamental battery technology are so focused on getting the battery to work that the overall integrated energy storage system that takes that battery at the heart of their system and wrap the controls around it, taking into account the specifics of the battery, is thought about later. So it's something that is an important thing that needs a lot of work on it. So thank you, Spencer.
Thank you.
Okay, Eva, the two more questions.
Okay.
One from Brad Price. You mentioned lithium ion invented by Sony, which has lightweight advantage.
No, Sony
And
did not invent it. Sony did not invent it. Sony
Okay.
manufactured it.
Okay. Let me see. The rest of the question is, I thought the lithium iron phosphate was more suited to larger scale energy storage. Can you discuss?
The lithium ion phosphate is what?
It is more suited to larger scale energy storage.
Well,
Grid scale, yeah.
well, it is it is becoming the most common technology now. And this gets into some very specific chemistry issues, which is not my area of expertise, but I could ask Taylor for her to provide more detailed information later. That, you know, it has a little more stability than some of the others, but I'm going to get into the safety issues later. That when you stuff a lot of energy in a little box, there are always issues to address. But I think the fundamental is that LFP is becoming the belle of the ball, is the main, you know, technology. There is a rating system for batteries too, tier 1, tier 2, tier 3, and for battery energy storage systems, you know, the recommendation is to use the tier 1 manufacturers. And I recently saw a list of them, but you can probably Google that and find out who's a tier 1 and who's a tier 2. But I know Tesla, as an energy storage system manufacturer, they are a tier 1, because there's battery tier 1s, and then there's, you know, my one of my pet peeves is that, you know, when people say, "Oh, I'm gonna go get a battery for my house," it's like, there's a difference between a battery system and a battery energy storage system. A battery or a battery system is a DC device, and a battery energy storage system is an AC device. And they are not very good terms, but it's the ones that we have been developed over time. And the only way we can provide clarity is for us to make sure that we use the right terminology and talk about what we really mean. So on this slide, which is about the technologies, it really covers all different kinds. You have the bottom, the electrochemical. On the right in the blue is the mechanical. The red is thermal. And then the green is chemical. So most of my discussion that is going to be talking about the electrochemical, which are all the different kinds of batteries. But in order to be able to make it suitable for the grid, you have to wrap around lots of batteries, balance of systems, which usually, has to include an inverter. Sometimes you need a converter and an inverter, depending on how you structure the system. And then you often need to have some kind of heating, ventilating, air conditioning, thermal management. And then you often need to have, safety systems too, to be able to, get it all in a box and then connect it to the electric system, to the grid, through all of the switchgear, protection, and transformers. So there's a lot of companies on this, and this is something for those that are in undergrad or graduate school. You can go and check out all these companies, and if they're still in business when you get out of college, you can go work for some of them. But there's about 110 of these, and and we work to test them, to evaluate them, and provide information to our utilities, kind of screen them so that in many different ways, so that we can work to advance them, to get them to a level of development so that they're safe, reliable, affordable, and clean. So that is kind of our landscape. And these are the attributes that we use to evaluate projects, which goes beyond a little what I said before, but if you notice, safety's first, it's at the top. We have to, consider the life, how long is it going to last? A typical utility asset has been 40 years. And in some cases, some of those nuke plants we were talking about earlier, they've extended to, another 20 years. But energy storage systems, have a shorter, usually they're designed for 10 years, some are 20 years, but then there's often a significant maintenance activity, whether it's replacing a inverter or the batteries, or augmenting them, or just totally replacing them. So those are all things that go into the life. Performance is essential and is probably one of the hardest nuts to crack. We are just launching a performance and reliability project now, because there's all these systems, but there doesn't have the same, it's not the same asset class as a lot of the other utility assets, such as transformers. We've been working to really make sure the reliability and performance of other utility equipment are as solid as they can be, and now we are applying those same practices to energy storage. So the other things you need to address, part of safety is environmental and public health, and this is really important due to some of the failure events that have happened, that people are afraid of battery energy storage systems, and so there are a number of municipalities that have put moratorium on deploying them for a year or two, so that they can make sure that the environmental and public health issues are attended to properly. So that really plays into siting considerations, and all of these Department of Energy projects that we've been working on are requiring community engagement plans, community benefit plans, and that includes, having the community understand it, understanding the technology to a point where they are understand the safety and environmental issues around it, and also that they can be a part of it and have workforce development, so that it's not just happening to them, but that it's happening with them. So those are quite a number of things on the technology attributes. And I'm sure you've seen these kind of graphs where you go through here we call it the valley trough of disillusionment. Sometimes it's called the valley of death. But the energy storage is different technologies are in different places along that blue dotted line. Lead acid and lithium ion are, and obviously pumped storage are the farthest along into the plateau of productivity. So this is really what our job is. You as students, as you move out of your education period into industry, you really need to work to push the energy storage through the trough of disillusionment, up the slope of enlightenment, and into the plateau of productivity. So welcome to the team. And I wanted to just give you one example of a technology that we've been evaluating. This is, Urban Electric Power. They're based in Pearl River, New York. The founder, Sanjoy Banerjee, was a professor or is a professor at City University. And he took your standard, AA D battery, which is nickel manganese dioxide, excuse me, and has been working and patented the ability to recharge it. So this is the company that I was telling you about that we have 2 government projects with. So this, gives you some specifics on it. Their round trip efficiency is between 65 and 80%. Their cycle life is 2,000 cycles. They have 2 applications, deployments. One is a backup power in San Diego, and one is a part of a microgrid with the Navajo Nation. And then we are working on these 3 other deployments in New York State. That will be 100 kilowatt, 10 plus hours. So, and I can show you when we get towards the end, another EPRI resource where you can get some information on some of the other companies we've worked with. So now I'm going to move into use cases. So you have this nice little energy storage box, and how are you going to use it? So any questions before I move to use cases?
There are questions, yes. So Bakish Yadav said, related to this, how feasible is it economically to store a huge amount of energy, lithium battery or any other battery?
How feasible is it, or how economic is it?
How feasible is it economically to store
Oh.
a huge amount of energy in lithium battery or any other tech battery?
Well, I think if it was really economic, you'd see it a lot more than you do now. And that has been the, a fundamental in the advancement of energy storage, and that is, that it hasn't been cost effective. And so the cost effectiveness is really something that is unique to the location, the application, and the rate, the tariff, and it's more economic in high energy locations than places where it's not. Although it's then might be economic there if you need power all the time. So if you're out at the end of a 100-mile circuit, and dad's on a ventilator and needs power, it might be worth buying an energy storage system to make sure that it's on because some tree's going to fall on that wire somewhere along those 100 miles. So there's different reasons for finding the money to install it. Now, one of the things that's really advancing it, well, 2 things is specific policy, legislation, regulation, and the other is larger and larger deployments of variable renewable generation. So you get wind out there, you get solar out there, and it really kind of wreaks havoc on some of the fossil plants that are designed to do some ramping, but not the ramping that is being caused by these, variable energy. Now, one of my favorite things to say, it's an engineering problem that needs to be solved. But when you have a fossil plant was designed 30 years ago with a certain operational profile, then you're going to, and now you're doing that 10 times a day rather than once a day. It's wear and tear on the equipment, and so you're kind of back engineering to make sure that that system is going to last the lifetime that you're expecting to. So it is feasible to store a lot of electricity, but at this point it's not economic and feasible. But who'd ever thought that every tool in your wood shop was battery based? I mean, you can still buy corded drills and lawnmowers and weed whackers, but I would say that people don't necessarily do that because of the convenience and the flexibility of having that battery based system. And over time that's going to be probably also for the electric system for all these reasons that I discussed up in the overview section. Cheaper technology, policy, both individual and company goals, and as we move to the clean energy future, we'll need energy storage to be able to help us cook our food after the sun goes down, so we can keep the lights on. So hopefully that answers your question. And you had other questions too, you said.
Eva, there's a question here which is very close to my heart. Any projects or experience with using energy storage to eliminate diesel gensets in data centers?
In data centers, I think you were at the advent of that. There are energy storage systems that are replacing diesel peaker plants. There's actually one that went under construction in Astoria, New York, which is part of Queens. It's been under development for probably 6 to 8 years, maybe longer, but they just broke ground on that, and where they're replacing the diesel peaker plant with a energy storage system. It's there's more and more data centers, in part because of AI. You need to have the data centers in order for them to do the machine learning, and so there's more and more of those. And I know that they're looking at energy storage, but they're also looking at some of these small modular nuclear reactors for dedicated Bitcoin and data centers.
Yeah.
So both of those technologies are being considered. In the interest of time, I think we need to move on to use cases, because we're just having too much fun here. So here we have kind of a basic table of the different location on the electric grid, transmission, distribution, and behind the meter customer. And the services down the left-hand side, and what can be done. And just because you can doesn't mean you should. But because the voltage support is something that the energy storage systems can do very well, not because of the batteries really, but because of the inverters. But when you deploy an energy storage system and you have the opportunity to use it for voltage support, that makes sense, but you don't put it in to do voltage support because there are other equipment that can do that. That is not so dear. That's more affordable. But anyhow, the colors show what can be done and what can't be done. So I just wanted you to see here a listing of the top battery storage developers and owners by operational capacity. And this goes, all over the world, not just in the United States. This is another data point from Wood Mackenzie. It came out a while back. And then on the right-hand side are nested circles that describes in power capacity and number of projects, who's the owner and operator. And as you can see, most of these in the US are developed and owned by a third party. And in some cases, that's true because of the policy. For example, I live in New Jersey, just over the river from you guys. And in New Jersey, utilities are not regulatorily allowed to own energy storage. And right now that's true in Texas and New York and quite a lot of other places. However, as the technology gets better and it becomes more important for the reliability, that you will probably see that change over the next 5 to 10 years. The other way that energy storage is used is in hybrid. Solar plus storage is probably the most common. Wind plus storage, as I think many of you know, that the US government's been auctioning off sections of the ocean to be able to put in wind, and there is hundreds and hundreds of megawatts going from Cape Cod, all the way down to DC. I think New York State probably has slated 2,400 megawatts at least of wind that's already on the books or installed. And so you're going to bringing that onto land and probably 4 or 5 different transmission substations. And if you really want to harvest all of that wind that's made, you need to have storage. Otherwise you might have to spill it, and we don't necessarily want to do that, because what's the point, right? But there's also been looking at fossil plus storage and nuclear plus storage. So this is one last Wood Mackenzie dense data that talks about solar plus storage projects, noting that there's 14.5 gigawatts that are in the pipeline right now in the next year, accounting for 60% of all system configurations, which is a lot. And if you look at the colors on the bottom left, California is a lot, but so is Texas. I mean, Texas has the most wind, and they are, needing the energy storage to help balance all of that. But this is actually, never mind, this is all solar plus storage. This is even wind plus solar. So California, Arizona, Nevada led the solar paired installations with almost 2 gigawatts installed, 78% of the whole market share. So I just wanted to go into deployment. I think for now we'll just wait to make sure that we have time at the end for any other questions. So what's in a BESS? So this is actually a real Duke Energy site. I can't remember where it is and what state it's in, but it's somewhere in the southeast. So all those 4 containers down the kind of in the center are the containers with batteries, modules, and the BMS, battery management systems, and the inverters. And then you have your thermal management, little gray boxes at either side. Across the top, you have deflagration vents. In the event that there is a thermal event or fire, they want to work so that it doesn't travel between the containers. So there is a required spacing between those containers. And then you can see kind of upper towards the top, the transformer, the interconnection, and the controls house. That's where you're going to work, Spencer. And of course, you have to fence all around it. So that kind of looks like what a standard large deployment. I think this was a 7.5 megawatt system, and I think it was like 11 point something megawatt hours. And then here's some other pictures of other systems, and EPRI uses the data from this to support our members. And then we also are working to try to harness this data in order to develop reliability metrics to help determine what the weak points are in the system. And I want to just talk about a couple of the challenges. I'm going to start with safety because that's always first. But what's really interesting is that EPRI has been tracking failure events for, I think, 4 to 6 years. I can't really remember. But as of 2024, there were 81 incidences, and 26 of them had information to assign a root cause to them. What's really, really interesting, if you see that hockey stick graph, there was, considering how many more megawatts or gigawatts of systems have been deployed, the rate of failure has gone down. So people have learned from the failures, which is very, which is really what this event database is all about. It's not to point fingers, but to say, okay, what happened? What do we do so that doesn't happen again? But there's still a lot to learn. DC arc flash hazards are really not well understood. Codes and standards are, just on a race, changing and updating in order to manage all the different technologies. And then there's a lot of public education with first responders and government officials that need to be done. But I wanted to note that this graph came out of this report, and when you get this PDF of this slide deck, my coursework here, that report, Insights from EPRI's Battery Energy Storage Systems Failure Database, is a free download, and you can read the whole thing. But I wanted to share another document about reliability. So, what is the leak, the weak point? And through the analysis of those 26 systems, which really isn't a lot, it's probably not necessarily statistics, but what we had, that it really was not the batteries, that the integration is really, and the assembly and construction is really the weak link here. There have been issues where the design is such that the way the vents were, let water in and got them on the batteries, and lithium and water go boom. There was, issues where the integrator used, really nice tier 1 batteries, but then, bottom of the barrel, sensors to run the HVAC system. And so the thermal management system stopped working and overheated. So it's really important that those who are procuring these systems, whether it's a utility or a third party, that they really take the time to know what they're getting and to ask for what they want. So, and then the other thing that's, something that we're trying to understand better, and we have a number of research projects, is battery degradation. And of course, every chemistry has a different type, different rate of degradation. And then even within the same chemistry, every manufacturer. And so we are working trying to understand it better so that we can then model it, because that impacts the life of the system, when you need to augment, or whether you overbuild, or you know, what is going to be the life cycle cost of that unit. So I just wanted to take a couple minutes on the roadmap. This is the battery energy storage roadmap. We issued this October 7th, and this is also a free download. Somewhere I think I have a link for you in here. If not, you can always just, use the magic machine and Google it. But this is our third version of it. And so what we're really focusing on here is, what is the energy storage vision for advancing deployment? So we did our first issue in 2020 and updated that in 2022. And this version has reviewed it and updated it and actually simplified it. So it looks beyond 2025 and improves its usability. And this is something that you can use within your coursework, or look to understand the types of issues that interest you, so that you can then go find a place in the world where you can address these gaps. But in regards to the organization of it, we have done this in a matrix fashion, because this is why I told you how we structure our research program. And it's basically, we'll have a graph in a minute with the actual listing of the gaps, which you'll be able to read later. Actually, I think you have to read that on your own. But we've sorted it by our research project sets and the EPRI mission, which is safe, reliable, affordable, clean energy for everybody, with a foundation on equitable trained workforce and innovation. So this is a tool that we use with our utility members to address the gaps that are priorities and important. But it's also a resource and a tool for you in order to develop your future, to figure out what you want to do your master's thesis on, and for Rudy to put questions on his tests. And then lastly, I have other EPRI resources that you can access. And this bottom left, Incubate Energy Labs, is an active link for you. So we have a program that we invite people to submit their ideas, their technology ideas, and energy storage is always one of the topics. And if you can see, we started this in 2019. This actually started as a DOE project, and then we took it over back then. And we usually have a couple of utilities and a couple of subject matter experts. So you can go back, I think it was 2021 when Urban Electric Power was one in the cohort. I think Zatara here is an energy storage technology. But they have, this is a free information on all the companies and their projects. It's a 1-year project, so it's got to be very clear and well defined. But it's a great way for these startups to find interested parties, as well as for the utilities to see what's new and interesting that might make a difference in their business. So that's one. And then we have a storage wiki site at EPRI. This is where we have access to the free use of the Distributed Energy Resource Value Estimation tool. That is a free download that you can use to do value systems. We also have a fundamental course called Energy Storage 101, which is not dissimilar to what you're getting right here. But I think our number one product is the best failure incident database, where we list where it is, what it is, and any public information that we can get. And we also have a vendor database. So that is something that you can access and include in your report that's due next week. And then we have the Energy Storage Integration Council, which is an open stakeholder group that advances the integration of safe, reliable, cost-effective energy storage systems. And how many times can I say that, right? But we have developed 17 free available tools for you to start your own energy storage business, everything from an implementation guide to a cost template, test manuals that's being updated right now, commissioning guides, fire hazard mitigation analysis tools. So all of these, if you go to the ESE website, all of these reports and tools are free to you to download and use. So that's your homework. The other thing is, just in case you have nothing to do on Thursday, the New York Battery Energy Storage and Technology Consortium, which is just up the road in Binghamton, we are having our annual Storage Technology and Innovation Conference, which is Thursday. If you guys are really interested in energy storage, I suggest you play hooky and not go to class, and you go up to this conference. We are having a poster contest with a grand prize of $3,000. Unfortunately, the entrance time is closed, but it will happen again next year. So Rudy, you need to remember that. I am the board chair of this organization, and I'll be presenting, and then there'll be 2 other folks from our team there also presenting. And if you can fit it in, that would be a wonderful thing. And now, Rudy, over to you.
Okay.
Is there any questions?
All right, very good. You loaded them with homework, Eva, and they're gonna curse me now. All right, so as we do in the past, I'd like to open the floor. First of all, ask the students to ask questions. And students, please unmute yourself and introduce yourself and ask a question. So I'm going to ask the students in the audience to ask questions. Go ahead.
Hello, my name is Sajjad Al-Shimmari. I am a student in ESE. I have a question. I hear there is a new technology about the sodium ion and nuclear battery. Is this possibility to change from lithium ion or not? Thank you.
Thank you very much for your question. Sodium ion is the next best thing. And there is a lot of work being done on that. I would say predominantly most of the R&D has been done in Asia, but there are some, a handful of companies. I think there's one in Ohio that's we're tracking. Go back to that nice picture of all those technologies that are working on sodium ion. And the energy isn't as dense, but it has a safer, a better safety profile than lithium ion. I'm not sure to see if they have sodium ion on there somewhere. I think we need to add that because that has been in the future, but now the future is now. So sodium ion is definitely something to watch and to see. And I can't remember which Chinese company, but I think they're expecting to have their sodium ion batteries commercial either now or sometime in the next year. So thank you.
Good question. Thank you, Sajjad. Any other questions from students? Please unmute yourself, introduce yourself. Okay, I'm going to ask the general audience if you want to ask a question orally, please go ahead and introduce yourself, or you can drop it in the chat box and I'll go through them.
Hello, I have a question. My name is Dylan Veach. I'm actually a Lehigh University 2016 and 2017 graduate in environmental engineering. I have a lot of interest in this side of things, and had I known about ESE, maybe that's what I would have majored in back in my undergrad career. So in my own like personal interests, I do follow Google alerts for battery technology, and I see all kinds of like emerging technologies like ceramic separators and carbon graphene separators to prevent thermal runaway, and like we kind of talked about sodium ion and other chemistries and solid state versus liquid. Is there like a good resource that like kind of compares all the emerging technology and tries to figure out like what would be an optimal one, or is it really up to like I guess the free market and people's ideas to try things out and see if they can move forward?
So that's kind of like asking what's the best chocolate. And the reason I say that is I don't even know if that's the best analogy, is that it's kind of like I like my other analogy. I'm like, go buy me a box. If I ask you to buy a box, what would you bring back?
Right.
So the thing is, the energy storage comes in different sizes and does different things depending on how you're storing it. So the best storage is compressed air energy storage, except that you need a lot of space. You need to have the land, you need to have the cavern. It's really, how you're going to use it. You can't use compressed air energy storage for that, it's
Right.
not going to work. So there is no best. I had an investor ask me that probably 15 years ago. I think it was Siemens. Siemens wanted to get into energy storage, and they were like, so which ones are best? I'm like, well, it depends. So I think the thing to think about is that when you're working on the energy storage system, you're not just doing it because it's a cool widget. It's like, how are you going to use it? And then you need to really have a clear understanding of how to get it to be safe, reliable, product to solve a problem. You're not buying energy storage because it's cool. You're buying energy storage to solve a problem. And so what is the problem that your technology and your configuration of that storage do? So, one of the things, the reason that we use, and I think I mentioned this earlier, that we use lithium ion on the electric grid is it's not really the best technology for the grid. But the utility industry doesn't have a lot of R&D money. Most of it really is in universities and government. Utilities do not have much of any R&D budget. When you think of companies like Coke or Ford, or Apple, the amount of money, when you buy one of these that is actually in R&D is percentage-wise probably 20 times as much, maybe 10 to 20 times as much as what utilities pay for it. So we're using lithium ion because someone else paid to develop the lithium ion battery and not the utilities. So now we're trying to advance these other technologies that are probably more suited for the electric grid, long duration, zinc-based flow batteries, those things that spin around really fast, flywheels, mechanical, thermal, trying to get to that same level of development that they did with lithium ion. And you think it's been who can do the math? Well, it's 40 years since the 70s. And some of these other technologies haven't been around as long. So they need a lot of money and a lot of smarts, and a lot of you brainiacs out there to go work on it.
Thank you.
Thank you.
Any questions for EVA? Either oral or chat box. I see a new message, and let me see that. Where's the question? Okay, Carlos, based on LCA analysis run by EPRI, what are end of life options for utility scale batteries?
Based on levelized cost, did you say?
LCA analysis run by EPRI. LCA, life cycle.
Oh, life
Life
cycle
cycle,
analysis.
yes.
Thank you. Obviously, can you tell I don't work in that area of what is LCA? Anyways? So in regards to life cycle, what is the what? Can you repeat this end of the question?
Okay, based on LCA analysis run by EPRI, what are the end of life options for utility scale batteries?
Oh, well, I know a couple of companies that are working on that. And we actually have done some projects, end of life. We did, I think, well, there's a couple of paths for that. The ideal one is for it to operate till the end of its planned life, let's say 10 years. But sometimes you have failure events. So we have a report called Carnegie Road. I think it's a free publication where we helped a failed battery system. I think it was in England or Scotland. And we wrote a report about it. So when you have a failed system, you pretty much you have to decommission and figure out where to send all the different stuff. But if it reaches either close to its end of life, then you have to figure out what you need to do. And so we also worked with Southern Company on a decommissioning, and we wrote a report about that one too, although I'm not sure that one's free to the public. Not to say that, you can certainly pay for it if you'd like. But for the most part, it's like, any old power plant, you decommission it and you deconstruct it and you figure out where the different parts can go to recycle them. So that takes us to lithium ion recycling. And as you all probably know, lead acid recycling is like a walk in the park. It's a fairly easy process. Recycling lithium ion batteries is not, partly because of how they're manufactured and the intricacies of their design. But there are, I think, 3 companies in the States that are working on developing recycling. There was actually a company, I think it was a Canadian company called Li-Cycle. And they were doing the hub and spoke, where they would have these spokes where they would collect them and they would take them back to the hub, and the hub was going to be Rochester in the old Xerox facility up there. But you need a lot of money for that, and they have been put on hold. So the intent of used energy, lithium ion batteries is to, take it apart and recycle as much as you can. Now, I'm not sure if your question when it came to what can you use with them afterwards is second life batteries, where can you take EV batteries and then do something to, because typically the energy within an EV battery, once it's used up its useful life in a vehicle, is only about 80%. And there are several companies, and I'm working on a report right now that'll be done by the end of the year, which you can download. And I can give when it's available, I can give it to Rudy so that you can read it if this interests you. About can we take those rejected EV batteries and make them into a stationary energy storage system? And you can, but the question is it cost effective? And I think that's the thing that we really don't know yet, whether or not. And also, as they get better and better will the battery manufacturers for EVs, value engineer it in order to have it not as much energy in it over time. So those are some of the considerations.
Thank you.
Thank you, Carlos.
Okay, questions from the audience? Put it in the chat box or ask the question directly, please.
Rudy, this is Jim Robinson.
Hi, Jim. Yeah.
I'm retired from Pennsylvania Electric Utilities and in the bulk power planning and operation business for over 37 years. Eva, I'd like your opinion as to whether we can get to net zero by 2050 if we use battery storage and nuclear to supply the energy that's required in the USA between the hours of 5 p.m. and sunrise. It's unclear to me how we do it and whether we can get there. What's your assessment?
Oh, that's a loaded question there, Jim. Where there's a will, there's a way. How's that? But it's kind of like herding cats. To get everyone. I guess to start off, the best electron used is the one you don't use. So the first thing to do is, if you don't need it, don't use it. Don't leave the TV on. Get yourself all LED light bulbs, all of that stuff. Move into a smaller house and have 10 people live in the big house, So, here in the United States, we have quite a rich lifestyle. But if we want to maintain that lifestyle, I think fundamentally the technology is there and that we could do that. But it's not the technology that's not going to make the difference. It's, the people, the communities, the governments, we are the government, but we have to work in a fashion that is collaborative. And we all have to have that same vision. So whether or not we actually make that, I don't know if you read any of the New York commentary, because New York State has some lofty goals and, this by 2040 and that by 2050. They want to put 6 gigawatts by 2030. And right now they have 1,300 megawatts. So they have a lot to do just in the next couple of years. The point is that there were some news articles that the government, the New York State government said that they're not going to make their 2040 goal of being, net zero. So I don't think there's an answer yes or no, but the answer technologically, I think, is yes, but it's really quite uncertain whether that could happen because of all those people and all the policies. And we don't necessarily, we are a federation of states, and so every state defines renewable energy differently. I don't know if you've ever been to the database of state energy efficiency and renewable programs, DSIREUSA.org, and there's a map, and you can find out, all the regulations and all the legislation in every state on renewable energy. And if you go in and look at the definition, they define it. Pennsylvania defines coal tailings, using coal tailings as part of renewables. Or at least they used to. I don't know if they still do, but they don't in New Jersey. So how's that for a non-answer, Jim?
I think that's actually where I'm at. Is I believe we technically can do it, but I don't think there is one miracle single answer like solar and wind plus batteries. I believe we're going to have to use all the tools we've got: solar, wind, batteries,
and some we don't have. It would be really nice to figure out how to extract the energy out of coal without burning it. So if you got a spare nickel, you can invest in that. I worked with a guy who was doing that at University of Akron, and he stopped doing it because no one gave money to do it. Direct carbon fuel cell. So that
you
was a
very
pretty
much.
cool idea. What was that, Jim?
Thank you very much. I appreciate your frank response. I'm in a very similar page, I believe.
Very good. And what plant did you work on?
I actually worked on Susquehanna Nuclear Plant, Montour Coal Burning Plant, and Martins Creek Oil Plant in PPL, in northeast part of Pennsylvania.
Yeah, I used to live in Towanda. That's when I worked for Penelec, and I used to drive by the Susquehanna. So, back to you, Rudy.
All right. Jim is a part of our advisory council, Eva. Questions for Eva? Either drop in the chat box or ask her. Questions, chat box. So while we're waiting, went on a field trip to Con Ed 2 weeks ago, and they made a presentation on their plans for their 70 by 30 plan, which is to decarbonize the grid 70% by 2030. And that's also very ambitious.
Yes, it is.
Yeah.
But you have to have a goal, right?
Yeah, you have to have a goal, yes. But there's so much interesting work going on in New York to Con Ed. It'd be really great, if they succeed, because I think they're really putting the effort towards it.
Right.
Questions for Eva? We still got some time.
Yeah, you mentioned that battery storage systems have a short lifespan. Do you foresee like the battery recycling industry growing in the future?
Say the end of that. You faded at the very end, Spencer.
Do you think that the battery recycling industry is going to grow?
Yes.
Good.
There's a real simple answer.
Yeah.
Yeah. And I don't know, short, it's a relative thing. The thing is, one of the projects we're working to help a utility decommission a system. It's a BYD system that, isn't supported anymore. I think it's been there 10 years. And what they really want to do is, take out all the old batteries, keep the containers, keep all the infrastructure, the interconnection stuff, and retrofit it with a different system. So this goes back to the other gentleman's question, what can you do with an old one? So, they're, and it's uncertain whether that is, the best economic deal, but, it's being analyzed right now. And so, can they take out those old batteries? Can they put new ones in there? Is the container, meet the right safety codes? Because when they put it in 10 years ago, it was a different safety standard than it is now. Can you fit, is it tall enough to fit the stacked, battery cabinets? So there's lots of things to consider, whether or not you can reuse them. But it's a great idea to think about it. Try it. I answered you a different question. Did I answer your first question too, Spencer? Can't remember.
Oh yes, thank you.
Question, we've got 5-6 minutes time for one or two questions. Eva, a question for you. If you had to make priorities, as a utility person, is it long duration storage the one that needs to be available soon, or is it storage at substations, so that they can handle behind the meter loads from electric vehicles and so on, in places where EVs have made a great penetration?
So, there you got a couple questions there. So the thing is we think we need long duration energy storage. We don't necessarily know that we need it, but we think we're going to need it. And then lithium ion, there are companies that are working to configure lithium ion to be long duration. So there are inconsistent definitions of what short, long duration are. Is it short, longs, or short, medium, and long? Because there's some that are saying, well, long is seasonal as opposed to, it's like daily, weekly, monthly, yearly. So all of those definitions are, the DOE has one set of definitions, but it's not actually different, because we actually looked this up. Different DOE groups, or Sandia National Lab has a different definition than NREL, the DOE. So all that kind of has to be sorted out, kind of like the naming of energy storage too. So it's not really certain, but it is certain that there are lithium ion, because they're like, why would they not do lithium ion? You put enough in there so that you can stack so they're only designed for 2 or 4 hours, but then you have the controls, Spencer's new job, to have them go on and off, so you always have this specific level for over 10 hours or 12 hours or whatever. You had one other question I didn't answer. Which one was that?
Well, about these behind the meter loads that could explode if
Oh,
there's large
right.
scale adoption of EVs. Yeah.
So actually, this is the report I was telling you about that we're doing with Second Life batteries, is also about the EV. So you're right. We need EV. We may need energy storage to be able to charge the EVs, especially the heavy duty trucks. And actually, we're working with a utility to look at mobile energy storage. Mobile meaning maybe more transportable, not necessarily mobile, so that you can take them to rest stops, because they're going to have to build the infrastructure, the wire poles at some point, but they're thinking that the electric trucks are going to be there before they can get the wires and poles there. So you get a unit there, and it's there for 3 to 5 years, and then do you take it to another rest stop and do that, or by then it's all the infrastructure built out so that you can use that transporter unit someplace else, and what would you use it for? But I think there is the opportunity for someone to really come up with a product, and there are some. Actually, I've worked with some. That was Incubate Energy a couple of years ago. Can't remember the name of the company, but that are specifically developing battery energy storage systems to support the charging infrastructure. But at the same time, and this is the report I'm working on right now, is like, well, then you have the infrastructure from the cars. Can the cars be used to support the grid? So
Yes.
you have it going both ways. And and it's not to say, it goes back to what Jim was saying, just because you can doesn't mean you should. The thing is, you have the electric vehicle, and is your battery on board? Is your charging infrastructure on board, or is it off board? So depending on where it is and what kind of technology is, and and you sign up to support the grid, and it's like, oh, dad has to go to the hospital, and I've been using it to support the grid, and I can't, he's having a heart attack and I can't get him there. Because people buy their cars to go places, not to support the grid.
Mhm.
So where's the line to say that can you only use the charge in the EV down to a certain amount, or do you only have fleets like buses, or post office trucks do, fleet support to the grid? Or, the other thing is like when the car plugs in, how do you know whose car it is and who do you compensate? So there's a lot of things that need to be worked on. Those are some of the research gaps that have been identified. If you download that energy storage roadmap, the last 2 pages, there's a list of all the gaps.
Okay.
So there's
Good.
companies you can start, and there are, opportunities to do work to fill those gaps. Thank
Good.
you, Rudy.
Well, thank you, Eva, and just a very enlightening lecture. And you have given us I'll be teaching the storage course 2 weeks from now, and I want to take advantage of all these resources that you have identified. And thank you very much. Next week we'll have a speaker from Australia, and so we'll be adapting uh, a suitable time to listen to the lecture. It'll be 3:30 instead of the usual 12 noon. It'll be the next day, early morning in Australia. He's also a former Lehigh student, and he'll be talking about the energy transition in Australia. So we have had energy transition in Uruguay and India, and we'll have another example of what's going on in Australia. Thank you all, and thank you, Eva, for this presentation.
Thank you. Happy to be here.